Yeah, let me give a short introduction of all the three papers today we're going to present. So for the first two papers, we will be focusing mostly on instruction tuning. Basically, we want to find the most, we can say, effective or influential data for instruction tuning for example, a specific downstream task or a set of downstream tasks. And Yijun will present the first two papers. And on the third paper, it's about like general selecting data selection for the pre-training phase, leveraging influence models. Okay, so Yijun, you can get started.
Yeah, thank you. Hi everyone. I am just a second, just something else. Okay. Yeah. Hi guys. I am Yijun, and today I'll be presenting two papers on data collection and how to scale these methods to large language models. And before I start, please feel free to interrupt me for any questions or concerns. And without further ado, let's get started. So data selection is the use of data attribution to select influential data for a particular task or maintaining model performance with much less data. And the motivation is the enormous cost and time training large language models. For example, the Llama 3 8 billion model requires over 1 million GPU hours, and we're facing human annotated instruction datasets of more than 10 million in size. And moreover, it is commonly believed that the datasets, and especially those used to fine-tune large language models, usually contain redundant data points and biased data points. So one question would be, can we maintain or improve performance with much less data points? So we have previously seen data attribution being used for tasks like mislabeled data detection. And here we can look at data selection as an extension of mislabeled data detection, where we can select data for multiple purposes and not just those that are mislabeled. However, common instruction tuning datasets often consists of millions of actual data points. And one question would be, how do we scale data selection methods to large language models? And the first paper I am going to focus on is the LESS, selecting influential data for targeted instruction fine-tuning, presented by Xia et al. And here, LESS means a lower rank gradient similarity search. So this paper mainly addresses the problem of incorporating training-aware and optimizer-aware data selection and how to scale these methods to large language models. And first, let me present the definition of influence. So in this paper, we are considering per step influence. So for a model theta of t that's trained on time step t on a certain loss, we can do a first order expansion of the loss. And here z prime is the validation point. And for now, let's assume that our parameter updates comes from a SGD optimizer. And as we can see here, the parameter update is just the normal gradient times the eta of t, which is the learning rate that is chosen at time t. And plugging that in, we have the definition of per step influence that is in this inner product form. And if we recall the classic formulation of influence functions, we can see that it is also in the form of inner product, which is in the kernel of inverse Hessian. And for now, in this paper, because we are only expanding to the first order, we can write the definition of influence in a normal inner product form. Are there any questions for now, like regarding the definition of influence? Yeah, great. So one problem with previous formulations of influence functions is that the training dynamics is not incorporated into the estimation of influence. But we can always ensemble the influence calculated across multiple epochs, and thus we can even out the error introduced by the position of a data point during training. And because each data point is used exactly once for each epoch that we train, we can use our previous definition of per step influence, and we can define our SGD influence as the ensemble over n epochs, where the big N is the number of epochs we train. And thus, we can be incorporating the training dynamics in the influence calculation. So we can just look at this as an ensemble over multiple model checkpoints. And another issue with previous influence calculation is that we cannot incorporate the optimizer we are using in the estimation of influence, because we're only considering normal gradients. And in other words, we assume that the parameter updates actually comes from a SGD optimizer. So what are the consequences? That we have a different parameter update. So here I am using the Atom optimizer as an example, which the actual parameter update is calculated by leveraging first order and second order gradient informations. And therefore, in our previous formulation of influence functions, we cannot incorporate this actual Atom gradient in the calculation of influence functions. But now we are considering per step influence, so it would be really trivial to incorporate this. We can just replace the training gradient, which is the delta L z of theta t, with the actual parameter update, which is the parameter update that is really done in an Atom step. And here we're using cosine similarities because usually instruction data sets contains prompts of various length, and it is often believed that using cosine similarity is a lot more stable than using normal products. But given these definitions of influence, how do we actually select the data? So step one will be the warm-up training, where we use lower rank updates on the model parameters. And this step can be seen as shifting the parameters to a neighborhood of the optimal parameters, so that we can take the training gradients. And here we're using lower rank updates because that can greatly reduce the number of parameters, and thus will make the entire process much more efficient. And step two will be computing the training gradients. And also here we are random projecting them to a lower dimension and from a gradient data store. And we also note here that we can use other random projections like those used in track, and that will be also effective. And the third step will be calculating the validation gradients, where we define as the average gradients over a few shot validation examples. So here, D of J val means the jth validation task, in which we select a few shot validation examples. And this could be, for example, a few example from the common instruction tuning datasets. And after computing this validation gradient, we use it to calculate the Atom influence, which is just by using the formula we have just defined. And finally, we aggregate this Atom influence using maximum. And this is intuitive because we consider a data point as effective if it is if it is effective towards a certain validation task. And after the score is computed, it's used to sample the data from the training set. And these sample data are used to retrain the models. And here are the results presented by the authors. On the vertical axis, we have the three models that we are interested in. And on the horizontal, we have the three usually used benchmark. So as we can see in the blue boxes, less is effective on multiple benchmarks across different model architectures. And with only 5% of data, we can achieve comparable or even more accuracy compared with training with full data. And also here we have in the orange boxes, the less T version, which stands for transferable, in which the data is selected using a smaller model, which is the Llama 2 7 billion model. And these data are later used for larger models like Llama 2 13 billion or models of different architectures. And we can see here the data selected usually have universal effectiveness, which means that the results are transferable. Are there any questions regarding the results and the data selection? Good, thank you. Well, one challenge of data selection is how to scale these methods to large language models, because we're dealing with instruction tuning datasets of over 1 million in size. So here we present the complexity analysis, and as we can see here, compared to previous influence functions where we will compute the inverse Hessian vector product for each training point, because we're considering only per step influence, we can compute the training gradients for once, and thus will speed up the process. And the bottleneck of the algorithm is actually the computing of the training gradients, which takes time that is equivalent to n epochs of fine-tuning. And comparing to other attribution, this method scales greatly to large language models in terms of time. And also, because we're considering a training gradient database, storage actually becomes a problem. But we can always overcome this by projecting the gradients onto lower dimensions. And moreover, as we can see here, because we are only comparing gradients of very low dimensions, the actual data selection takes really less time. And we have talked about incorporating the optimizer used by using the atom gradients. So how effective are the atom gradients compared with the normal gradients? So as we can see here in the blue boxes, by using atom gradients, we can actually achieve higher accuracy compared with only using vanilla projected gradients. And also, as we have talked before, in the calculation of influence, we are ensembling across multiple model checkpoints. And we can see here, this ensembling is actually very effective. As we can see here, by training over 4 epochs, we can achieve much higher performance over random selection. But our data selection is also robust because when trained over only 1 epoch, we can still outperform the random selection. And if the last paper I presented is focused on selecting influential data points to maintain or improve performance over specific tasks, The next paper I'm talking about, less is more, data value estimation for visual instruction tuning, is placed in a more general scenario. And the motivation is, when pre-training, we're not really focused on the improvement on a certain validation task. Instead, we're more focused on the general improvement of model ability. So a common situation is that we are facing multiple training datasets that are targeted on several tasks. For example, they can be instruction tuning on a vision language model, and we're considering for example, figure caption generation, or VQA. So how do we actually sample when we are faced with multiple and diverse datasets? So in this paper, the authors are interested in vision language models, and the influence is defined to be the norm of gradients, which is not usually familiar. But the intuition behind this is that now we are not interested in improving the performance over a certain validation task, but rather we're more interested in the general improvement of model abilities. And thus, data points that shift the model the most will be considered the most influential. And thus, we can define the norm of gradients as the influence. And here, by gradients, we mean the gradients taken with respect to the projection layers between the encoder and the LLM and the large language model output layer. And we take the gradients with respect to these parameters because it is commonly believed that these layers contain valuable information about predictions. And one question we might face in terms of this situation is, how do we determine how effective one dataset is? And for example, if the figure generation is much more important than the VQA task, then intuitively we should sample more from the first dataset. And they also used this task level value to measure this, and it is defined as the average norm of gradients. And also, after we have determined how many data points we want from each data set, how do we actually choose these data sets? And the author used the instance level value, which measures how effective one instance is within the entire data set. And here, S stands for a certain instance within the ith instruction tuning, the data. And it's defined using the similarity between the gradients and the average gradients across the entire training set. And this is intuitive because we consider a data point as effective if it can provide a similar parameter update compared to the average of the entire set. Are there any questions regarding the definitions of these two values?
Yes, Yijun, I have a clarification question is, which model are this, are these gradients calculated from? Because you're talking about there are multiple tasks and multiple data sets. So what is the model that we are calculating the gradients from?
Oh, yeah, thanks. That's a great question. This model is actually the VLLM, in which in the original paper, the authors actually experimented with multiple models, but we are interested in a multi-modal large language model in this particular scenario. Yeah. So
Right.
in which,
my question, sorry, my question might be, so is this model trained on the data sets we are trying to estimate their value, or is this like, or we are basically have some pre-trained model, and then we're just using it to estimate maybe some data set that doesn't appear in its training data set?
Yeah. So I think in the original setting, the large language models are actually pre-trained on these data sets, and we are selecting the data sets and thus train from the base models, and then evaluate them on the same tasks. So basically, the large language model or the visual encoder we're considering here have already been pre-trained on these data sets, and now we are selecting the data to pre-train them for other model architectures. So that's the setting of the entire problem. And thank you for the question. And one question would be, given these two values, how do we actually select data? And the first step will be determining what portion to sample from each of the sets we are interested in. And this portion is defined to be a normal mean pooling of the task level values we have defined before. And intuitively, the more important a set is, it will have higher task level values. And thus we are sampling more from it. And the second step will be how to actually sample the data instances. And as we can see here, the score is calculated using both task level value and instance level values. And the involvement of instance level value is really intuitive, because the higher instance level value is, the more likely we're choosing this instance from the entire set. But here, we're also considering task level values because for data sets that are more important, we will want a more sharper, we will want a sharper distribution sampled because we would want as much influential data points as possible. And on the contrary, for those data sets that are not important and thus have a low task level value, we're looking for a flatter distribution. And that's because we're looking for more variety for sets that are not so important. So here we can see the entire pipeline is a trade-off between a sharper distribution and a flatter distribution, and a trade-off between influence and variety. So after the data set are chosen, they're used to retrain the model. And as we can see here on the y-axis is the relative accuracy compared with training with full data. And on the x-axis is the pruning ratio, which is the amount of data we exclude. So this metric is pretty similar to the brittleness we have seen before. And from the figures, the labels are different data sets that are used to pre-train the models. And as we can see, we can maintain over 90% of total accuracy with only 15% of the data. And also, the authors provided the ablation studies for dataset size and hyperparameters. So in terms of the dataset size, the authors are interested in, does the final training set affect the relative performance? And as we can see here, even only with as little as 12K instruction tuning instances, we can still maintain over 90% of total performance. And also, the authors provided the ablation studies of the temperature of which controls the sampling distributions here. And as we can see here, the entire pipeline is robust to the selection of temperature. And to sum up, this paper places the data selection in a more general scenario where we are more interested in the general improvement of model abilities rather than the improvement over a certain validation set. And so that's all on my side, and thank you all for listening.
Hello, Yijun. Can I ask a question?
Yep.
Yeah. Could you like reshare your screen?
Oh, I'm
Yeah.
sorry.
Thanks.
Yeah.
Could you go back to the page that the instance level like score is defined? Yeah, one slide before. Yeah, here.
Yeah.
I was like a little bit like wondering about the intuition about the instance level value here. So, if you can like consider the case that you have a data set and you have like a large groups of data sets that are very similar to each other, and you have like two small groups of outliers, which so after the like the calculation of gradient, like it's likely that due to the like calculating this calculation and because like this cosine similarity is likely to select the like the major parts instead of like focusing on the outliers. So I was wondering if if it is really like intuitive, like how whether or not this instance level value will ignore those outliers or like such value.
Yeah, that's a nice question. You're right in that this calculation of instance level value will ignore the outliers within a certain set. And this is because in this paper, we are not actually interested in extracting the biased or mislabeled data points. And we believe our data sets to be of general good to our models. And thus, we are more interested in decreasing the size rather than selecting, probably like excluding the biased or mislabeled sets or those outliers. Does that solve your problem? And also, sorry for interruption, but and also in the actual sampling step, we can see that if a task is more important, we are more likely to choose like the grouped part you talked about because we consider those grouped parts to be most influential to the model. However, if the task is not important, we will be looking for a flatter distribution, and thus we might be more likely to choose those outliers for more variety. So I think this is a trade-off between the influence and the variety. Yeah.
Yeah,
Does
like
this solve your problem?
yeah, actually, like just a small follow-up that you said that like you are assuming or like this task is assuming that like more most of the data points are like contributing or something like that like to the prediction. Is that like a common setup in this kind of training? Because like I'm not really familiar with that. Yeah.
Yeah,
Okay.
that's also a good question. Yeah. I think like in this setting, we are more interested in decreasing dataset size because we consider like the bulk of the dataset to be beneficial for our models. Yeah.
Yeah. Thank you.
Yeah, thank you. Are there any questions regarding the two papers that I presented? Yeah, thank you all for listening, and I'll let Huang take over.
Great. Thanks, Yijun, for his presentation. Can you see my screen now? Yeah, I believe so. Okay. And for the last paper, we will be discussing this paper, the MATES model-aware data selection for efficient pre-training with data influence models. Okay, so for the motivation for this, we have actually a very similar motivation as the previous papers. There are a lot of available data sources that we can crawl from the internet for the pre-training phase for large language models. But however, the bottleneck here is that we have very limited computational resources. So we need some methods. At least we're motivated to select the data that are most useful. We will define what does it mean by useful later in this paper. Okay. And the second motivation is that most current selection methods for the most useful data relies on heuristics, and this heuristic does not take into account of the training dynamics in the pre-training phase of the language model. Okay, and in this way, the authors propose the dynamic data selection in this pre-training phase. And here is another more intuitive visualization of the fact that the data influence that we probed at different pre-training steps are actually very different. As you can see in this heat map, for both y-axis and y-axis, where they're showing the different training steps. And for each block, we're calculating the correlation of the data influence at different steps. And on this from left to right, the cross axis, the correlation is of course 1. But on the other side, for example, if we're thinking about the data influence correlation between the first 10K in the first 10K steps and the another 10K steps after that, the correlation is actually only like a 0.4. So which means that we need a dynamic method to adjust the selected data instances, and also a dynamic way for calculating the data influence based on the training steps. Okay. And here is
just to clarify, so here when you say the correlation of data influence, you are suppose you are like fixing some maybe validation data points, and then you calculate the influence of the training data points on those validation data points, and then you calculate the correlation of the training data influence scores between two different steps. Is that what is down here?
Yeah, I believe in this paper, in this specific experiments, the author didn't use a reference. I think they didn't use a reference data sets. I believe they just use a fixed data set and calculate the data influence for the data points at different training steps.
So is that self-influence, or is that because when you're calculating data influence, you got to be the influence of the training data points on something?
Oh yeah. Yeah, I think like I didn't recall that Asa specifically explained this setting, but I believe that might be one of the. Yeah, sorry for the misunderstanding, but I believe it may be one of the reference data that they use later in the paper.
Okay.
I think that's the setting. Yeah.
Oh, thanks.
Okay. Yeah, because this is actually not one of the major results of this paper. It's just a motivation experiment. Yeah. Okay. And here it is the major pipeline for this paper. So for the objective, let's first focus on the blue part. We want to maximize the target performance of a specific model, and we are constrained by the computation flops. And at the beginning, we have the main model, right? And we do not have any training here. And we first, on the first epoch, we first train with random data. And after one epoch of training, we collect the data influence based on a reference data sets. And we then train the data influence model. And we use this data influence model to further guide the training on the next epoch. Basically use this data influence model to calculate the data influence and choose the most influential data points. And then after this part, we actually then again calculate some data influence and updating our data influence model. And this data influence model will be afterwards used to select the most influential data points for the next epoch. And for the ease of computation, we're actually in the actual algorithm, we're not collecting the data influence on every epoch, but on a certain interval. And we're updating our data influence model upon a certain interval to avoid the actual computation of the influence model on every epoch. Okay. And on the next few slides, I will be focused on the actually objective, the definition, the formulation of this problem about how to maximize the target performance. Okay, so on this page, I will be giving a formal definition of the data selection at each epoch. So the target here is to find the optimal batch, a batch of data on each epoch. And this batch is come from the argument to find the best batch of paper that minimizes loss. And let's focus on this loss function. So the DR here is a reference data sets that are collected, which is a held out data set from the training set. But also this reference data are actually sampled from the same distribution as the pre-training data set. And we're minimizing this loss on this reference data based on this A and B. So the M here indicates the model state, and the B here is the batch of data that we're trying to find. And A here, the A and B here actually means the optimization of this model on this batch B with one step of training. So basically, as a whole, to understand this formula, we're trying to find the best batch that after one step of training on this model that can minimize the loss on this reference data sets. So if we can, think about like if we have unlimited resources, we can enumerate all the possibility of this of the selection of this optimal batch, right? Which will be exponential. If we enumerate all the possibilities and actually train one step for each of them, and we calculate the loss for the reference data, and we just select the choice of this batch B with the smallest loss, and we will regard that batch as the optimal batch for this for the data selection at this epoch. Yeah, do you have any question regarding this formulation? Yeah, I think the major takeaway is here. We want to find a batch that minimizes the loss on this reference data, and the definition here is very comprehensive. But the difficulty here is actually the computation, because we actually cannot computate all the possibilities. So we need some approximation methods that will be introduced in the next 2 slides to actually approximate this loss function so that we can find the optimal batch. Yeah. Okay, so if there are no further question, I will move on to the next slides. So the challenge here, so this is the formula taken from the previous slides. The actual challenge here is that to find the exact B, we need to enumerate all the possible batches, which will be exponential to the size of this batch, which will be prohibitively computationally expensive in this case. And the second challenge is that we need to calculate the we may need to calculate Oracle data influence for this reference data, which will also be not practical in the scale of a pretraining a language model. So to tackle these challenges, the authors propose two techniques to calculate the optimal batch. So the first technique is point-wise data influence, which is proposed, I think, by a previous paper. So basically, to calculate this, to calculate the loss function of this one step of training on this reference data set, we're actually approximating this loss by summing up the point-wise data influence of all the xi in this batch. So think about like each xi will contribute a little part, right, of the influence on the final reference data sets. So I think one previous paper showed effectiveness of this approximation, that we are basically assuming that there are no like core influence between this specific xi. So we're basically summing up the influence of all the single data points on the final reference data set dr here. Yeah, so that's the first part. So in this part, we are basically like reducing the problem from exponential to a linear way, in that we're just summing up considering all the single data points. But the challenge remains that we will not be able to calculate Oracle point-wise data influence in a very strict sense. So the second technique will be that we will parameterize this data influence. Basically, we will use another BERT-based model to approximate this point-wise data influence for every single data points. So again, the motivation is that computing the Oracle point-wise data influence will be very computational heavy in our case. So we'll need to use another model to actually predict the data influence here. Okay. And instead, we also propose that they can fine-tune a small data influence model. So here is the data set that will be used to train this data influence model. So basically, this is like the normal XY pair, right? The X is one specific data point, and the Y here is the Oracle data influence that we collected. For this reference data points, and here we introduce another data set, the held out data set. So basically, we are basically choosing the xi's in these held out data sets as the xi, and we will somehow collect a small subset of the Oracle data influence on the reference data sets. So in this way, we basically collect the XY pair for the training of this data influence model. And let's recall in this pipeline, we're actually talking about the second part here, the data influence model. So for each main model, we first collect the data influence model on the held out for all the held out XIs and calculate their Oracle data influence somehow. And then we train the model influence, the data influence model. Okay, great. And up to this point, I believe that's the major contribution for this paper. Basically, we first formally define what is the optimal batch at each apple, and then the authors propose two techniques to approximate the data influence, and then approximate that we can actually propose approximate algorithms to find optimal batch. And up to this point, I will be on the next few slides, I will be introducing the experimental results that demonstrate the effectiveness of these algorithms. And I want to stop here to see if you have any questions or comments on this pipeline. Yeah, okay, great. So I will move on. And this part is about like the how we're going to probe the local Oracle data influence. So basically here I eliminate another lengthy derivation that is very, very similar to the original influence function paper. But the takeaway here is that the author derived it here that this Oracle data influence will be proportional to the negative of the loss of this I mean, recall that the AMXI here is optimization of the model M on a specific data point XI. So basically, we can use this loss of this a one epoch training of the data point XI on this reference dataset as an approximation for this Oracle data influence. So I'm skipping all the math here, but I believe this is the most important takeaway that we can derive here. This is something that we can derive with a very similar mathematical derivation as the influence function. Okay, so yeah, I mean, if you're interested, you can take a look at their original paper. Okay, so yeah, and for the actual algorithm based on this derivation, basically for each xi in the held dataset th, we run a one-step training or one epoch training and collect the loss, and use this loss. We take the loss as approximation for this data influence. Okay, and here I'm showing the experimental results to illustrate that this method is effective. So basically, the authors we train the model on two like open source large language models called Pythia. So they do the experiments on this 400 million parameters and also 1 billion parameters version of this model. And the proposed method is called the maze, which is shown here. And this is all the data sets and also the average score. I think the first major observation is that the proposed model is very effective according to these experiments, both on the smaller version or the large version, the 1 billion version. And also another thing that we can pay attention to is us also show the flops of the training for this different model selection, data selection methods. And as you can see that even if the authors introduce actual computation because they need to calculate and approximate the data influence, right? that maybe account for like 20% of the total flops, but the actual total flops are actually reduced because the proposed methods is effective. And here the two score here are referred to the 0-shot and 2-shot evaluation here. So they have two numbers for all the datasets, for every datasets. Okay. And for this experiments,
one question I have is when they are doing the selection, are they using this dataset as the reference? I mean, this task, data from this task as reference, or
no, it's a held out dataset. It's one held out datasets.
okay, but like, are the tasks? I mean, are the data come from this task? Is it like, for example, do they use maybe one task during the pre-training and then evaluate on all the tasks, or
oh, I see.
Use exactly this 4 tasks during the pre-training selection as reference, and then evaluate on these tasks?
Okay. Yeah. Let me recall. I believe that is. I kind of need to refer to original paper. I believe these are all the downstream tasks, so they cannot be pre-trained. The language model cannot be pre-trained on this. So this is just for evaluation. I think the original model is pre-trained on the piles.
Right,
so they probably
for the reference, right? Because they're using some reference set,
right.
To calculate the influence score, and then so although like this cannot be I believe this data set will not be used in pre-training, but they could be used as reference for
you're talking about the reference data set, right? So your question is whether the reference data set is used at this specific data set, right?
Right.
So yeah, so the reference data sets are not one of this evaluation set. So they use an extra data set as the reference, as the DR in their formulation.
Okay,
right.
Got it. Thanks.
Yeah, thank you for your question. Okay. And on this slides, the authors are comparing the selection, a random selection, and their mates selection. So the x-axis, so let's first take a look at the A figure here. The x-axis is the training flops, and the y-axis is the average downstream accuracy, which is basically this column in this table. So I think the major takeaway is that if we select the data points that used in pre-training effectively, we're basically reducing like the flops to reach a certain accuracy by half, approximately. So and also this is the first figure is in terms of the flops, the actual computation that is needed. But for the B figure, where we use the training steps, which might be similar, and I think a very similar takeaway is that if we select the data points effectively, we can reduce the actual steps to reach a certain accuracy effectively, and also even we may be able to improve the final accuracy in this training process. Okay, and I think the next 2 slides will be about some ablation study and some interesting ablation study the author proposed. The author showed in this in their paper. I think the first one is that the major takeaway is that the Oracle data influence is not very sensitive to the batch size. So basically, in their paper, the authors need to collect Oracle data influence by the approximation of the loss function that we introduced previously. So, but how can we actually calculate this? We can have different ways, right? We can do this one by one, or we can calculate the batch of this score and use another algorithm in their paper to separate influence in that batch. So basically, in this figure, we do a correlation study of the influence scores for different batch size. Batch size equals 1 is x-axis, and the batch size equals to 16 is the y-axis. So we basically calculate the correlation and report a experiment here. And as you can see that these are actually super correlated. So yeah, so which means that the data influence, the Oracle data influence calculation is not very sensitive to this batch size, as long as we're doing the calculation for the same model state here. Okay. And another, yeah, this is actually, I think, answering Jiaqi's question about the reference data sets. So in their paper, the author actually used this lambda dataset as the reference data sets. And these other two datasets are just for reference, just for this, just used in this specific ablation study. So I think the major takeaway is here that if we calculate the correlation between the performance on this reference datasets and the performance on average of all the downstream datasets, we find that actually this specific dataset is actually more correlated than the other two datasets. So it means that choosing the most appropriate this reference datasets is actually very important for their pipeline, right? If we accidentally choose, for example, these two datasets, then the influence scores may not be very instructive, or meaningful to instruct the selection of the pre-training data points. So, but I think maybe actually you can use, if we're actually using this algorithm, we can first do this ablation study to select the most reference task and reference datasets, and then use this reference datasets for the training. So basically, maybe in a small scale, do a pre-selection step and select the most effective one. Yeah, and up to this point, I think the author also introduced a few more ablation study to demonstrate the effectiveness of their algorithms. And if you are interested, you can refer to the original paper for the details. Yeah, I think that's all of my presentation on this paper.